So dear participants, let's come down to the second bit of this programmable logic controllers unit 3. So here we will be particularly concentrating on the syllabus aspects. In this particular lecture, we will be covering the aspects of PLC addition, PLC subtraction, multiplication and division. This PLC repetitive clock, I thought that I should cover, but later onwards I could find that it is not there in your syllabus. So even if it is there, that is not that important right at this moment of time. So this addition, subtraction, multiplication and division are the basic mathematical operations that needs to be covered, and therefore I'll be concentrating on the same first. Now you see that these math functions, whatever they are in the PLC, that allows it to perform the arithmetic values. Now uh, whenever we are talking of arithmetic functions, those functions have to be performed on some values. So you can see such values have to be stored in memory words or registers. Okay, this is one important aspect that you should remember. That whatever the values are there, that should be stored somewhere, because unless it is stored, the PLC will not be able to perform the arithmetic functions on such values. Okay, so we have given here an example where you are using a counter. Okay, the counter is used to keep track of number of the parts which are manufactured, and there is a display, and this display is responsible to show us that how many parts must be produced in order to reach a certain quota. So you can take the thing in such a manner that in a particular batch production, a certain quota requires 100 parts to be produced. Okay, so these 100 parts to be produced, that is there in your mind, and or the plant supervisor, and he wants that there will be a display, so that each of the part that is manufactured, when the part has been manufactured and certified, then what will happen, that display will show that initially it will show 100. When one part is manufactured, it will show 98. The other part is manufactured, it will show 90. First part, after first part it will show 99, then after that it will show 98, then after that it will show 97, like this. So every time the workers who are working in that particular batch line, they will be sure that how many more parts are required to be produced in order to complete this batch. So here what is required? Definitely a counter is required. Now the accumulated value of the counter, what is the accumulated value of the counter? Once each of those part, whatever they are produced, once they pass through the counter enable bit, then what will happen, that the counter will start accumulating like this, 1 2 3. Okay, and what you need to do, you need to store the value of 100 at some memory location, from which you are to subtract continuously the accumulated value of the counter. So once you keep on subtracting the accumulated value of the counter, then what will be the output? The output will be like this. It will be 99, then it will be 97, then it will be 99, then 98, then 97, then 96, like that. Okay, so these things have to be displayed. So this is the basic operation. So here you can find that this particular operation reads mathematical subtraction function. So this is how the arithmetic functions are required to perform various day-to-day tasks in industrial realm. So we can find that there are basic 4 mathematical applications. Okay, the addition, subtraction, multiplication and division. Now you see that most of the mathematical instructions, they take 2 input values. Okay, they perform the specified arithmetic function on these 2 input values and output the result to an assigned memory location. This is one big advantage with PLCs, that whatever the values they have been stored, they are not disturbed while keeping the result. Okay, the result will be kept in some other memory location. This is very sure. And in case of 8086 microprocessors, you might have seen that there is one source and one destination, and once the mathematical operation is performed, then one of these 2 sources is disturbed and here your result is being kept. Okay, so now you see that here it is not the factor. The two input values will be located in different locations. The mathematical operation will be performed, and finally the result will be stored in a third memory location. This you need to be very sure of in case of PLCs. Now you see here, uh, whatever the math instructions are there, they use the contents of two words or registers and perform the desired function. This is one important factor. Two words are used. Why two words are used? Because we have already seen that whatever mathematical function will be there, they will be performed on 16 bit of data. Then what is the necessity of two words? The necessity of two words is that one word is assigned to define which operation has to be performed. This is one important concept that you need to remember. When you are using two words for one instruction, then one word will be assigned to specify the instruction and other word will be assigned to specify the data on which this particular operation has to be performed. Now you can see the PLC instruction for data manipulation, that is data transfer and data compare. They are used with math symbols to perform math functions many times because it is required. Data transfer or data compare operations, many times they should be coupled with mathematical symbols in order to perform complex operations. That is also possible. An important aspect that you should remember, that whatever math instructions are there, they are all output instructions. And this is the figure you can see you can see that this is the RS Logics particular sector of menu tab. This is RS Logics 500 menu tab, and you can see the compute or math particular function, they have been highlighted, and whatever you are having in front of you, they are very clear. This is compute, addition, subtraction, multiplication, division, square root, negation, then this BCD, I should say transfer formats. Okay, so let us see what are the commands. First one is CPT, compute, that evaluates an expression and stores the result in the destination. Next, there is addition, which adds source A to source B and stores result in the destination. Then there is subtraction. Here you need to be a bit considerate because it subtracts source B from source A. So here source A is the primary one, okay, from which we need to subtract source B. Again the result will be stored in a third destination. Then in the multiply, it multiplies source A by source B. Then there is divide, it divides source A by source B. So always remember that source A is the primary one on which there is source B which has to be subtracted from source A. If you have got a source B, the source B divides the contents of source A. Whatever the contents of source B, it has to be added to the contents of source A. So you need to remember that way. That will be a bit easier for you because many times it comes into confusion for us. Subtract करना है, A से B को करना है या B से A को करना है. Always remember A is the primary data. Okay, so here whatever the things are, they are subtracted from whatever there is in source B, they are subtracting from source A. Whatever there is source B, it is added to source A. Whatever there is source B, it is multiplied with source A. Source A means what are the contents of source A rather. Now you see there is also a square root function. In the square root function, it calculates the square root of the source and places the integer result in the destination. Here you can see the integer result is placed in the destination. So there is a round of factor that the PLC takes care internally, and finally your integer value is placed in the destination. Next is negation. Okay, that changes sign of the source and places it in the destination. Then there is this conversion to BCD, okay, that converts a 16-bit integer source value to BCD and stores it in the math register or the destination. Here there is conversion of a BCD value to the integer value, and again the result is stored in a math register or it is stored in a destination that you have specified. Okay, so these are the basic mathematical operations performed by a PLC. Let us start now with the addition instruction. First of all, you see that this is the ladder logic program. So this is the special block for addition instruction. Okay, there is one, this you can consider this just as an enable input. So whenever the switch is on, the addition is performed. So it is not that it will always be switch over here. The switch is just for representation purpose. I must say that when the rung condition is true, when the rung condition is true, then your addition function will be performed. Now you can see here that source A, it is defined with the address N70. Source B, it is defined by the address N71, and the destination has been defined by the address N72. So in source A we have stored 25, source B we have stored 50, and therefore the destination is having the value of 75. Okay, now you can see one particular thing that is very important to consider here, that how these values are accessed, because here we have got 25, here we have got 50, and this 25 and 50, how will you get that? So now you see that whenever you are performing the laboratory experiment, when you are simply performing the laboratory experiment, then you can put these values. Okay, you can put these values. Now it is not always the laboratory experiment you are performing where you have a keypad to put the values. What happens actually, that if there is some analog input or some particular means by which you can get the decimal data. Now you can see most of the input devices, I will also show you some of the input devices. The input devices, they do not allow decimal data. If it is a BCD thumb wheel switch, then it is not possible to get the this decimal data, right? So under that circumstances, the BCD has to be converted to decimal and then it should be placed here. So what happens, that whenever some analog input platform is there which we are taking at some of the input bit, so whatever that input signal is coming inside the PLC, that input program is stored in this N7.0, and from which you can get this particular value. So many times it happened that students, when they perform such type of experiments in laboratory atmosphere, they do find it very easy. Okay, just to put 25 here in N70, in N71 they put 50 and they get the result, it is so happy. Okay, it is a, because things are easy na. But when you actually get into the industrial atmosphere where we need to put some data inside this register through some means in the input port or through some of the timer or counter, then it becomes a bit difficult for them. Therefore this is just for an I should say explanation to you, for an easy illustration to you, but actually the thing is not that easy. Now you can see we will talk of an illustration. Okay, here let us be very considerate to the conditions of the application that requires an addition instruction. Here you can see then we have an application that requires a pilot light to come on when the sum of counts from the two counters is equal to or greater than 50. So now you see here we have got two counters. Okay, what is your output? Your output is a pilot light. You have got two counters, and again there is a condition. This is the conditional application where when the sum of the two counts, they are equal to or greater than 350, then your pilot light should come on. Okay, so now you should start thinking in this manner, that since there are two counters, we need two different addresses where we can store the accumulated value of the count. Then we need to add it, whatever the result of the addition, that has to be stored in a different destination, and then that contents of that destination has to be compared with the value of 350. Now this 350 cannot lie virtually, it has to be stored somewhere also. So these are the things that you should remember. Okay, now let us see what we have done here. Source A of the add instruction is addressed to store the accumulated value of counter C5.0 or 50. Source B of the add instruction, because we have got two counters now, it is addressed to store the accumulated value of counter C51. Now you can see the value at source A is added to the value at source B, and the result is stored at destination N71, right? So the value at source A, it is added to the value of source B, and the result is stored in N71. Now you can see source A of the GEQ instruction is addressed to store the value of the destination N7:1. Source B of the GEQ instruction contains the constant value of 350. So as we have already discussed, source B of the GEQ instruction, because GEQ is greater than or equal instruction, this is a compare instruction. Okay, as I have told you that if you look at a mathematical instruction A plus B or A minus B like that, then I will take only 5 minutes to complete this entire thing, because I will just show you such type of block and I will complete my discussion. But unless these mathematical implications, they are, or mathematical for these functions, they are collaborated with other operations in the PLC, there is no goodness of learning this particular aspect. Okay, so here we are this collaborating this particular mathematical function with counter function as well as compute this compare function. Okay, so source A of GEQ instruction is addressed to store the value of destination N71, and source B of the GEQ instruction contains the constant value of 350. So 350 has been stored somewhere, and source A, it is this destination address in 0.71. Now you can see what is source A and source B. Source A and source B are the two inputs to the comparison block, because whenever you are to compare, you need at least two data. So these two data are constituted by source A and source B, which are feeding this compare block. Now you may wonder that why we are not taking separate address, because we are directly taking this destination address N71. Why we are not putting one of the data to N70, then the next data to N71, and finally the result is stored as N72, what we had earlier assumed. Now you can see that the accumulated value of counter 5.0 has to be stored somewhere, but accumulator is the place where the data is already stored. So why to take another bit of data? Why to make the PLC more busy, or why to waste the memory? Because the accumulator of the counter has its own address where data can be easily stored. So the accumulated value is stored already in the accumulator in both cases, and then we can add both of them and use N7.1 or 7:1 to store this content of the addition of the two counters. So this is the goodness of having separate address for accumulator. Now you can see the GEQ instruction and PL1 output will be true whenever the accumulated value in these two counters are equal to or greater than the constant value 350. Definitely there should be a reset button to provide a capacity so that we can reset the accumulated count of both the counters to 0. Let us see now how the this ladder diagram will look like. You can see over here, this is one proxy, this is another proxy. So through proxy 1 materials are passing, through proxy 2 also materials are passing. Okay, whenever each of the material is passing through the proxy, then what is happening? The accumulated value is getting incremented one by one. The same is there for this second counter also. When each of the materials is passing through the proxy, then this accumulated value will get incremented. Now you can see this accumulated value is getting stored in this particular address, which is the address of the accumulator. Here also the accumulated value is stored in this address of the accumulator. Now you can see in this particular addition instruction what we are doing actually. We have written for source A, we have written C50 ACC, right? This means that the accumulator contents of C50, contents of the accumulator of counter 5 will be source A, and here contents of the accumulator of counter 5 1 will be source B. Okay, so this and this has to be added. Now when both of them are added, definitely you need a destination. So here you have given the destination N71. Now let us come to the compare block. So whenever we are talking of comparison, we need at least two data. Okay, so this is source A and source B. So you can see here the source A, it is N71, and source B, as we have discussed already, it is containing that constant factor 350. So when it is greater than or equal, then this particular output coil will be energized or activated. So whenever this is higher or equal, then this will be activated and your PL1 will be glowing. Okay, now you can see that this see the rung conditions. This rung, continuous rungs are there. Okay, now you can see this proxy is present here in form of a switch. So whenever this switch is activated, activated means this switch, I will just give this thing, whenever one material will be plased, this switch will become contacted, and whenever there is no material, then what will happen, that this switch will be open. So when this contact is made, that means this normally open switch is closed, then your count will be incremented by 1. Now you can see over here that your addition instruction, there is no enable input for the addition instruction. What does that mean? That means that your addition instruction is always under activated condition, it is always under enabled condition. So whatever the values are there, addition will be carried out in continuous manner. You can see here in our earlier slide, we had put here one switch. What was the purpose of that switch? When the switch is activated, that means this normally open thing becomes closed, then the addition will be performed. But here there is no switch, that means the addition is always ready to be performed. Whenever the data is changed, the destination will have a reflection of that. Now you can see the same is there for the comparison instruction also. There is no enable bit. Okay, that means the construction is comparison instruction, sorry, this comparison instruction is always ready to compare the data that it receives at this source A. And finally we have got a reset switch. We can see this is a reset switch, and this reset switch, they are going to the reset terminals of the two counters. Why it is required? Because if we want at any moment of time to reset both the counters to 0, we need to just what we need to do, we need to push the switch. When the momentary push to on switch, when the switch is pushed, then this normally open becomes normally closed, and your counters are completely reset. So whatever values they were accumulated in the counter, they become 0 again. So this is how the addition instruction is performed in this particular application, where we have collaborated this addition instruction with counter operation as well as one comparison operation. So I hope you understand this addition operation.